Allow me to reintroduce myself. My name is...
What does this remind you of?
Schrodinger's cat.
Wow.
Wow. Okay.
When all of these tools come together, it's a powerful combination.
It's amazing.
That's amazing.
It's an entire suite of different kind of possibilities.
Hi, I'm Gemini.
What neighborhood do you think I'm in?
This appears to be the King's Cross area of London.
Together, we're creating a new era.
Welcome, everyone. A warm welcome to this particular live webinar on LLMs. So the story of AI isn't just about building a bigger models. It's fascinating chain reaction where every single breakthrough was born from a frustrating problem. So each great architecture we have today, from the first RNNs that tried to remember to the transformers that learned to pay attention, wasn't just a random idea. It was a targeted solution to a roadblock that held the entire field back. So today, we are going to follow the story, seeing how a particular solution has been brought, how solving one problem created the next, and how that relentless cycle of innovation has brought us to the incredible models we have today. So let's dive in. So basically, we will start with the vanilla architecture. From vanilla, we will look into the most advanced Gemini diffusion architecture, and we'll see why and where and what to solve what problem we have taken the next one. Yeah, so let me introduce our S-Kid. So will be part of this live webinar, and he would like to understand all these things in detail. Is a very curious mind.
Yeah, hi Charan. So let's get started. You said neural networks, right? So
Yeah, I
what
would like
exactly are
to.
these neural networks?
Yeah, we have a presentation to put on, so let's try to get this up.
Okay.
So meanwhile, yeah, so I would like to understand. Yeah, so basically, so are you curious? What is your curiosity at this moment? What would you like to know more?
Okay. So uh, first of all, everyone's using LLMs. Everyone's using the new Gen AI stuff, but no one understands how it came to be. How did we, from making normal algorithms to normal formulas to this great Gen AI stuff that even I'm not able to comprehend? How did we get here exactly? Unmute.
So that's what we'll be exploring today, from vanilla RNNs and vanilla neural networks, and from this we will be deep diving into the each and every architecture and why we have developed this, and then what problem it has solved, and finally we will also look into the most advanced present architecture of Gemini Diffusion 2. Sure, let's begin now.
Yeah. So, what exactly are these neural networks?
So you would like to understand what exactly is this vanilla neural network?
Yep.
So, so think of it as a foundation of everything that we know about deep learning. So, why do we call it vanilla? Because it's the simplest, most basic form. Just like the vanilla ice cream is the base flavor that probably you would like more, what does it consist of? So, as you can see on the screen, the particular image, so you can scroll up a bit to find the entire image in the viewport. So now in this particular image, what you see is are three essential layers. And most of the data scientists know about this. The first layer, which is labeled as X, is the input layer that receives data. And at least one, a basic neural network. So in at least one hidden layer we will have, which is again represented with H, and that process the information and it converts it into a nice mathematical numbers, and you have an output layer that actually produces the result and that decides which label it is. Okay, so these are the three layers are connected by neurons and that pass information forward. We will use the feed forward neural network in the overall. So this is where our entire AI journey begins. The feed forward neural networks, the feed forward is the one which to uh, pass the information, and then you will have the backward propagation is to correct it and to make it the most efficient. So this is what the basic vanilla neural network, the base flavor.
Okay. You keep highlighting vanilla. So, I mean, that means it is the version 1, right? So, what are the limitations of this that we had to come out of it and develop further?
So you would like to, okay, basically you would like to, so we need to go back to the times where we got the vanilla neural networks at the initial stage, and then from there, so basically the base is vanilla neural network, and from there we have added the more hidden layers. If you add the more hidden layers, it will become a deep neural networks. We call it as DNN, and that's a one flavor of it. And similar to that, if you go one step ahead and convert them into a CNNs, which is convolutional neural network, it has been used for extracting the features from image. So we call it as spatial feature extraction, and that actually revolutionized and created a new complete application layer, which is uh, computer vision. So these are the two additional flavor enhancement that we can see in vanilla neural network. One is deep neural network and other one is convolutional neural network. Yep.
Yeah. So, what are the limitations of this that we had to develop further?
Okay, so that's where the actual game starts, I think.
Okay.
So the we have this artificial neural network, then first, what are we doing with this artificial neural network? So that's what the first question that comes. So we can move to the next slide, please. So the first, using artificial neural network, it's very simple. Here, what we're trying to do is, example, if you take the convolutional neural network, it's basically classification. One of the problem that we're solving out is the classification or object detection. Okay. So similarly, you can use an artificial neural networks for the regression algorithms, for the prediction algorithms. So whatever it could be, the fundamentally what we are trying to do there is the fixed input size or the fixed outcome. So prediction labels by and large would remain same all the time. So these are fundamentally incredibly rigid when it comes to data size. What does this mean exactly? So that's what I've been giving examples. They only work with predetermined sizes. They take fixed size inputs and must produce fixed size outputs every single time. So why is this a problem? Because the world doesn't work in a fixed sizes. How can you translate a 10 word into a 12 word sentence when your network expects exactly the same input and output dimensions? Are you trying to get my point? What I'm trying to make? When you make a regression, example, a linear regression, okay? So your input can consist of 8 features: x1, x2, x3, x4, x5, x6, x7, x8. And your output will be one, which is y. So it remains same. So your input is always, it should be 8 features, and your output is always y, which is 1 feature. So it is fixed input and fixed output, which can only solve a one type of use case, where probably a regression, a classification of something. But when you need to do a machine translation from English to Hindi, or from English to Tamil or Telugu, it could be anything where there are no a fixed input. Because when you are doing a translation, you won't be giving the same number of tokens all the time. It is not possible. So one sentence consists of 10 words, other sentence consists of 50 words. It is impossible. It is impossible to run these models for machine translation. So this is the biggest problem that we have. We are in the era of vanilla neural network. I'm not talking about now, when we have invented the vanilla neural network. So that's the biggest is, how can you translate a 10 word sentence into a 12 word sentence when your network expects exactly the same input and output dimensions? So this fundamental limitation led to the development of more flexible architectures. So the question became, how do we handle the variable length sequences such as one to one, one to many, many to one, many to many, many to. So this is fundamentally what I'm talking about is your input you give to the model and what it predicts, the output. So this is very important thing. Majority of the people won't even touch. See, now what we are trying to touch upon is not being touched by 99% of content creators in AI. Do you have anything else?
Okay. Yeah, like you said, the real world doesn't work in fixed sizes. Uh, so I have a doubt. So did early AI researchers try to pad or truncate the data to fit these fixed sizes for our practical implementations? Also, what are the downsides of such method if they did so?
Yeah, so yes, they would patch shorter data, or even they're truncated this longer data. So because we need to run the show at any cost at that moment with whatever the possibilities we have. So the biggest downside of this is critical information was often lost. So, and it forced a rigid, unnatural fit for dynamic real world data. And that's the reason these models are not good with the machine translation. So, however, we used to have a machine translation before also. So now we see, now we are in 2025, we are in a different era where you have the text models which are doing crazy. But we are discussing about an era where we just got an artificial neural network, and what was the condition, what was the issue. Because see, here what we're trying to do is we are trying to understand from where we have started, what was your initial neural network, and now we have come to different stage where we are making a diffusion models. So what are the issues, what we have solved, how did we get to this stage? So these are the steps we are discussing and measure. Unfortunately, majority of the content creators have neglected it completely, because until unless you know what you have done before, you will never able to do it in a much better way in future.
Yeah. Now that you explained it, I understand why we had to move away from that padding wala padding techniques to our LLMs that we are using right now. So, uh, how does this fixed size input really mean in practice?
Yeah. So I think this is next. Yeah, we can move to the next slide, please. So the network. So first, let's try to understand, because as we were discussing about the fixed size input and output in our previous slide, let's try to understand what is fixed size altogether. Okay. So
Yeah.
now the network expects inputs that always have a specific predetermined number of elements. Think of it like a form. What exactly a 10 blank fields? You must fill all 10, no more, no less. Whether your data naturally has 5 elements or 50, you have to force it into the exact format. So this flexibility become major roadblock for real world applications. Can you scroll down a bit so that we can show the examples of fixed size inputs? As you can see on the screen, the fixed size inputs. So for an image classification, a vanilla neural network might require images to be resized to fixed size 224 cross 224 pixels. It was a major headache for me when I was building computer vision models. It's not too far. Even just 3 years back, this was the issue. Okay, you got these many images, some image of this size, some image of this size. So I need to have a common size of all the images. That's the most important pre-processing that we need to do. So that's what is called a fixed input size. And we were also working on sentiment analysis just 4 years back. Now we need to have a maximum length of 140 characters, or padding shorter tweets with zeros. You have to do a lot of stuff all around because it's fixed input size. Our models can only handle the fixed input size. And coming to the genre prediction, that's very famous machine learning projects those days. So your audio samples to be represented as a fixed length vectors of 1000 there. You don't have any other option at that moment. So that's what is fixed size input. Yeah.
Yeah. Can you also elaborate on the output side?
Fixed size output. That's next slide.
Yeah.
So when it comes to the fixed size output, again, the network always produces outputs with a fixed number of elements, regardless of what that input actually contains. It's like having a machine that only dispenses exactly 3 coins every time. So whether you need 1 or 10, this constraint actually severely limited what early neural networks could accomplish, especially for tasks involving natural language or time series data. So now if you want to see some examples, we can just scroll down over there in that particular slide. So let's take for the image classification. A vanilla net typically outputs a probability distribution over a fixed set of classes. Example, a cat, a dog, a bird, a tiger. Beyond that, it's not possible. That's a fixed size output that I'm talking about. Is this a problem? Yes, of course, it's a problem for the big things that we want to achieve. If it is okay, if you just want to do a classification between 3 labels, that's absolutely fine. But we don't want to stop over there. We want to reach to a different level. Is this a problem? Yes, of course, it's a problem for the bigger use cases. For the classification labels, it's absolutely fine, but we want to achieve much bigger things. So now when it comes to language translation, a vanilla net might output a fixed length sentences in the target language. Even the input sentence has a different length. So even for the language translation, you will get all the time of the same length of sentence, irrespective of the whatever the input sentence is. Is this a problem? Of course, it's a problem. So then you have the stock price prediction. Of course, there in the stock price prediction, probably you want to get the same length all the time. That's fine. So in some use cases, it's good. Some use cases is the biggest stumbling block. So now we need to solve this problem. We need to solve it at any cost because we want to achieve much bigger. Yep.
Okay. I understand the input. I understand the output. So, how did this machine learning actually work in the early times?
So, so basically, if you see, even the powerful convolutional neural networks share this fundamental trait. Okay, what is that? A fixed input, a fixed output. What 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 were they good at? Of course, they're good at. They excelled at classification tasks, predicting if an image was a cat, dog, or tiger. That's fine. It's all good. But why did this work? Because the set of possible answers was always predefined and finite. But but here's the biggest limitation. They could not handle the dynamic, variable nature of real world data unless the AI is not getting into the human life, not getting into the real world data, not impacting the every inch of human, it can't completely inflicted into the human lives. And that's where the biggest limitation is this. So this is where the story gets very interesting because the world demanded more flexibility. Yeah, I hope
Okay.
you got the point.
Yeah, I got the point. So, we're talking about classification. Beyond classification, were there any early attempts to make this model more variable output, like to handle more
Yeah.
variable outputs, even if they are clumsy? So, if they did, then what did those attempts look like, and why did they ultimately fail?
See, the best use case that we can take it. So we are always wanted to make a mission translation, language to language. That's been a dream. So IBM has been doing it, some or other thing, but it's not that great enough as we are now. Okay, so every solutions like statistical mission translation chain together fixed outputs. Basically they chain a multiple fixed outputs, and then but of course they struggled immensely with the context and natural language flow, so yielding rigid, often awkward results that lack true understanding. I think, see, I have been, I don't know. I don't know whether I can use this. I can use this name. So basically, I've used a particular model 5 years back for the translation. We were working on sentiment analysis, and we just wanted to translate Hindi to the English so that we can do a better sentiment analysis. And the output that we got is fundamentally was because it's statistical machine translation is what it's using in the back end. Just 6 years back at the starting of my career, like after 2 years of my career. So that's what it's direct example because I've seen the basic machine learning algorithms now to the diffusion. Yeah.
Yeah. Can you elaborate more on what actually happens when you deal with real world data? Because you said you have experience in it, right?
So specific to this particular example, the machine translation itself, you can take it. So when if you take a language, okay, audio, and the financial data, these are all sequences of varying lengths. The example that I've given is a language, and Hindi to English, a sentiment analysis that we want to do. And similarly, we're talking about an audio between the doctor and the patient. So now, how could a model translate a 10-word sentence into a 12-word sentence? This was the biggest challenge. So handling cases with variable inputs and variable outputs is becoming very difficult. For that, what new architectures did this require? So we needed a one-to-many relationships, okay, And like generating caption for an image is one example. So as we have seen in our previous slide, I put one to many, many to many. So similarly, just one to many relationship. An example is generating a caption for an image. And similarly, you have many to one. Example, the best example is sentiment analysis. You will have a big sentiment. It could be 10 lines, 3 lines, 4 lines, 5 lines, but still your outcome should be whether the positive sentiments or negative sentiments or neutral sentiment. That's many to one. These are the use cases we have worked, but we were not that efficient because of lack of high-end handling of these variable inputs or output sizes. Then you have the many to many. The best example for the many to many is like machine translation. So the fixed size paradigm simply could not handle these scenarios. And that's where the evolution truly begins.
Okay. You highlighted the challenge of translating a 10-word sentence to a 12-word sentence. So, from a
Exactly.
practical standpoint, what was the most frustrating real world application that could not be solved until variable sequence handling became possible?
So without doubt, as I've been repeating multiple times, a fluid mission translation. The mission translation, and we have been suffering like anything. And of course, out of excitement, I used to try multiple models that are available. So I'm just quoting the name. It's IBM Watson. I used to try there at the long back. That's the one which used to do, and Google, some model from the Google. But at the end of the day, uh, okay, so for some cases it used to be good, but at the end of the day, it's at a disappointment in front of the management. Still, that's okay. We have seen all those things as a data scientist. People used to mock us. This is what machine learning can do. This is what AI can do. AI will obviously will completely collapse after some time because you can't even predict the things well. It is just training and training. But now we are in a different stage. After some time, we'll be in a different stage. So I've seen all the things in my life, and this is one of the utter disappointment I have faced at the end. Finally, I have not used that particular model, and we have stopped that because it's not that efficient at that moment. But now, in the same company, they are doing it in a brilliant way, literally brilliant way. So now
Okay.
languages just don't map one to one, making natural translation effectively impossible until we could handle variable length sequences. That's very, very important. Until you have a variable length sequences, AI can't collaborate with human. If it is not able to collaborate with human, and you can't enter in the world.
Okay.
Yeah.
Uh, Now I understand all the limitations of the vanilla model. So, what was the breakthrough solution though? How did we solve this?
So I think we can get into the seventh slide. So let's talk about the most important one that we used to be afraid as well as excited, the recurrent neural networks. So those days, if someone knows about the recurrent neural networks, means he's a great guy. I'm talking about the 4 years back. If somebody has worked on recurrent neural networks, he's an ultimate guy. Of course, I got an opportunity to do it because I worked with a few time series models as well. So now recurrent neural networks, first proposed in the 1980s, introduced something revolutionary, a loop. Okay. So how does this loop work? You can scroll a bit down so that they can see the recurrent cell clearly. So an RNN processes a sequence one element at a time. Try to understand this in much better way so that as we go ahead, when we get into the transformers, this some of the information will be useful. Okay. So this an RNN processes a sequence one element at a time using its own output from previous step as input for the current step. So what exactly is happening? Regression and auto regression. So what makes this special? So this creates a memory. The network can remember what it saw before. So that's the additional benefit than compared to the normal neural network that we have. So why is it called an autoregressive? This is very important. If you know regression, what is regression? Regression is fundamentally you have the prediction label, which is y is equals to m, which is your most important parameter, and you have capital X, which is your feature. Y is equals to mx plus c, your constant. That's your regression. Now, if you have X, the feature is your previous value. That's your auto-regression. Here is the map. So now, why is it called an auto-regression? Each new prediction depends on past predictions. Think of it like telling a story where each sentence is on what you already said. I've given one example with using a feature, but when it comes to the actual auto-regression of recurrent neural networks, it is basically each new prediction depends on the past prediction, which is nothing but y new is equal to m into y t minus 1, the previous one. That's what is called autoregression. Why I'm repeating is you need to understand autoregression to understand your LLMs, to understand your transformers. But I'm sure majority of content creators, they never mention autoregression because they don't know, and that's what the presentation and they make YouTube videos. So now think of it like telling a story where each sentence builds on what you have already said. So this was at that moment revolutionary because it finally allowed neural networks to handle sequences of any length. Thanks to the RNNs. The RNN would just keep processing one element at a time, maintaining context throughout the entire sequence. Yes, kid.
Yeah. So before we move forward, I understand that this loop creates memory. That's a powerful concept. So, is there a simple analogy to describe how an RNN forgets older information, even with this memory?
Yeah, so basically, think of the telephones as the message passes through many people. RNN steps. Okay, the small details get lost or distorted with each transfer, so causing the original information to feed us. So this is basically how the loop loses some stuff, or we can say that how it forgets the older information, and that leads to a one basically this leads to one of the important aspect of issues with the RNNs, which is vanishing gradients.
Okay. Uh, so I understand the concept, but what are the practical implications of it? As in, what practical problems could this RNN finally solve?
Okay, so basically you would like to understand the RNN applications. That's what, right? Yes.
Yeah.
Can you go to the next slide, please? So now let's try to understand, as we have discussed, some of the use cases we are unable to solve with the existing neural networks, mental neural networks. Okay. So now machine translation became possible with many-to-many RNNs. You feed in the original text sequence and it produces a translated text as output. How about sentiment analysis? So that's a perfect many-to-one application. You feed in text to be analyzed and it produces a single application like positive, review, or probably a negative review or a neutral review. So the next question is, why were these applications so significant? Because they represented the first time we could handle, read, we could handle real world, very length data, and this actually opened up entire new domains for AI applications that were previously impossible with fixed size networks. And what I would like to say is, this is the time I got a complete confidence that we are going to take over this world using AI, and soon this world will be AI enabled.
That's a very great statement, and I think it's more nearer than we think.
Yeah.
But can you elaborate on what was the major flaw of RNN?
Okay, so basically, so probably we need to move to the next slide to understand the major flaws specific to the RNN. So the major issue in short is, I would like to say, the failing memory. That's what the major issue. See, as I've been telling, the initial basic issue is we are unable to solve the many-to-many or one-to-one, one-to-many, basically specific to the mission translation or sentiment analysis, and that's the reason we try to make RNNs specific to the many-to-many RNNs. But again, we are facing one more issue. Though we got this one, still it is not that efficient enough. What is the biggest issue? The failing memory. They suffered from the vanishing gradient problem. I think majority of data scientists will by heart this vanishing gradient problem for machine learning and deep learning. That's a very important question for an interview. So what does this mean? So information from early in a long sequence would degrade as passed through the current loops. The vanishing degradient. So the vanishing gradient. So it's degraded completely. Now, through the how bad was this problem? The memory of an RNN was frustratingly short, so it could remember recent information but would forget important details from earlier sequence. That's biggest issue. Now, why does this happen? So, as I told you in earlier slides, we use a feed-forward network to pass the information, and we use a backward flow. Backward network is to adjust the gradient and to make it efficient. So now, as gradients flow backward to many time steps during training, they get smaller and smaller until they virtually disappear. So this made it impossible for the model to learn long-term dependencies. So if you needed to remember something from the beginning of a 100-word sentence, the RNN would like to forget it by the end. But our dream is to read a 100-page PDF and convert that into a different language. Would it be possible with the RNNs? Not at all. It's failing memory. Yep.
Okay, I understand. So, if gradients vanish, does that mean the network effectively stops learning for the older parts of the sequence? As in, could you give a more concrete, relatable example of a task an RNN would utterly fail to because of the vanishing gradient problem?
Yeah. So it's learning from the distant past. A classic failure, linking a pronoun he back to a name the professor mentioned many words earlier in the complex sentence. So the memory just wouldn't stretch because it's very simple logic. When there is a huge sentence and the context between the pronoun and the professor is no more memorized and no more it's able to reflect their context. So that's the concrete example, and we are at that time trying to dream about taking the entire PDF and process it. So just imagine what we can do with that. So we need to work on to bring much better things.
Yeah. We have vanilla RNN now. So why do we need more complex architectures?
So that's where I've been telling in the previous slide. I think we need to move on to the next slide. So if we have vanilla, because the basic RNNs have fundamental limitations that prevent them from solving real world problems effectively, quote unquote, effectively, efficiently. So what are these limitations? The first one is short-term memory, vanishing gradients, and inability to capture long-range dependencies. So the question became, how do we build networks that can actually remember important information over long sequences? So this led to more sophisticated memory mechanisms.
Okay, so what was the solution then for the long-term memory that you speak of? What was the game-changing solution?
So that we will look in the next slide. So which is fundamentally an LSTM, as you're saying, it's a long short-term memory. You want to have a short term which is longer. So, so in 1997, Sepp Hochreiter and Jürgen Schmidhuber introduced the long short term, okay, long short term memory network, or we simply say it as LSTM. So how does this work? It's an RNN with a sophisticated system of gates. So basically what they've done is they've added additional layers, which are gates, an input gate, a forget gates, and an output gates. So what do these gates do? They allow the network to learn what information to store, what to update, and what to delete from its memory. So now our simple RNN has becoming a little more powerful by handling these information in a different layers. One information will come, okay? This information will be split or sent into three gates. One is input gate, other one is forget gate and output gate. Output gate is completely on the other side, and then input and forget what amount of information to be kept out, or an amount of information has to be updated and has to be taken forward to the output side. So why was this so revolutionary at that moment? So even now we can, LSTM is very useful for a lot of use cases. It largely solved the vanishing gradient problem and enabled learning of long-range dependencies. Think of it like a smart secretary who knows what information to file away and what to throw out and what to keep on desk for immediate use. So this breakthrough enabled applications that required understanding context over much longer sequences. I hope you got it.
Yeah, that smart secretary analogy for the LSTM gate is excellent. Could you elaborate on a scenario where the forget gate is particularly crucial? And what kind of information would an LSTM choose to forget?
So let's take this. The forget gate is key when context shifts. So in a review, like the service was bad, however, the dessert was divine. So it learns to discard the negative service sentiment at lower, allowing the model to focus on the new positive information.
Okay. What came after LSTM then?
Yeah, so that's what we have. I think from 1980s we have come to 2014. in our journey at this moment. So now we can move to the next slide. So in 2014, researcher including Kyung Cho and Joshua Bingo introduced the gated recurrent unit. We call them as GRU. How is it different from LSTM? So what they've done is your LSTM is a little complicated architecture. So what they've done is they have much simplified the GRU, but always my LSTM is my favorite because I've done brilliant projects with that LSTM. Yeah, so the GRUs, it simplified the architecture by combining the forget and input gates into a single update gate. You got the forget and you got an input and made it as a single update gate. So what's the advantage? So GRUs, you can just scroll down so that we can see the architectures of both. So GRUs often perform comparably to LSTMs, but are more computationally efficient. So they are faster to train and use less memory. So that's the advantage of GRU. So why does this matter? Sometimes simpler is better. The GRU proved that she could get similar performance with fewer parameters and less computational overhead. This became important as models grew larger and efficiency became crucial. Yep.
Okay. So you mentioned that GRUs are performantly more efficient. So are
And
there
it's fast.
specific types of tasks or data sets where architectural specification of GRUs actually leads to better performance than LSTM, not just comparable?
Says, let's take this example for smaller data sets or tasks with less complex dependencies. Okay, the GRU's efficiency can prevent overfitting and sometimes even lead to marginally better real-world performance due to the reduced complexity.
Okay.
Yep.
What's the sequence to sequence model?
That's very important. So that will lead us to the most advanced stuff. So that we need to move on to the next slide. So it's by the people. So thankful to them. In 2018, 18, it is specifically designed for translation tasks. How does a sequence to sequence work? It turns one sequence into another sequence using recurrent neural networks. Often, again, we're still with LSTMs or GRUs. So your RNNs remain in the picture to avoid vanishing gradient problems. So that's the fundamental idea of doing the sequence to avoid vanishing gradient problems, but still our fundamental base architecture is a recurrent neural network. Either it could be LSTM or it could be GRU. So what is the architecture? So it consists of an encoder that processes input. If you scroll down, so you got it consists of an encoder that processes the input sequence and a decoder that generates output sequence. And this encoder and decoder is gonna revolutionize the tomorrow's AI, but that time nobody would have imagined, even me. So why is this that important? It established encoder decoder pattern that would become fundamentally to many AI applications, from translation to summarization to conversation. I hope you're getting where we're leading.
Yeah, I understand that the encoder decoder pattern is fundamental, just like you said. So, how did the researchers decide on the number of RNN layers for the encoder and decoder? Was it trial and error, or was there any theoretical insights guiding this thing?
To be frank, a lot of things are a lot of things are trial and error. This is specifically largely trial and error. it was driven by the intuition first. That's why you need to have an expert data scientist, an expert uh, deeper experienced person, so that you can bring that intuition and trial and error to get the best out of it. So it was driven by the intuition that deeper networks learn richer representations. So balanced against the computational resources available at that time.
Okay. Uh, how do we apply this sequence to sequence architecture to chatbots?
Yeah, that's a great question. Actually, we are coming into the most important one. We can move to the next slide. So, sequence to sequence chat uses same and decoder architecture for conversation. What happens? So your encoder processes your message and generates a context vector, which the decoder uses to produce a response. So this was one of the first successful approaches to building conversational AI systems that could handle variable length conversations. And slowly we have started with the fixed size input and output, and now we are talking at the variable length conversation. So we have moved so far.
Okay, so finally, what revolutionized translation?
We can move to the next slide. So neural machine translation. Neural machine translation uses sequence to sequence models. You can see on the picture, specifically you have the decoder and you have the encoder, and at the time you have RNNs has been used nicely over there. Either LSTM or GRU has been used in the part of decoder. So neural machine translation uses sequence to sequence models to translate text from one language to another. How is this different from older approaches? Instead of handcrafted rules and statistical models, NMT learns translation patterns directly from data. Much more natural and translations that can handle context and nuance better than previous methods.
Okay, I know that we moved to LLMs. So, what new problems emerged with LSTMs and GRU networks that we have to move forward?
Yeah, that's a great question, and that leads to a different era altogether. So we can move to the next slide as we
Oh,
are already moved of the old era.
okay.
So even with their improved memory, because all we were doing from artificial neural networks, we came to RNNs. From RNNs, we don't have a high amount of memory. Then we started working on STM, and we want to make it simple and less complex. We have built GRU. So we have improved the memory for LS and GRU, but face the context bottleneck. That's very important at the end of the day. So what does this mean? Entire context of the input sequence had to be compressed into a single fixed size context vector. Essentially, the final hidden state, as you can see on the screen. So why is this problematic? So this information bottleneck made it difficult to handle very long sentences and nuanced context. So details would inevitably be lost in compression. So think of trying to summarize an entire book in one sentence. You are going to lose important information. This limitation becomes the next major challenge to solve.
Okay. So, as you said, if the context bottleneck is like summarizing an entire book in one sentence,
Yeah.
what was the practical consequence? did the model just generate nonsensical text, or were there any specific types of errors they made due to this information loss?
Yeah, so I think this is a brilliant question. So we should explore. Now, the practical consequence was lost nuance and long-term coherence. Models often produced grammatically correct but contextually inconsistent or very generic text, so unable to recall specific details from the long inputs. So that's what the biggest issue with those.
Okay. I have a question. So, how
Yeah,
do we make networks focus on the important words specifically?
yeah, that's what the question. No, it's not your question. We can move to the next slide. This is everybody's question those days. So everybody was worried about that. Everybody, literally everybody. Now you can give it more attention you need. So what we need, as you were asking, what what your question was, how do we make these networks focus more on important words? So you can put more focus on that particular image. So that was your question. So now you can scroll up, please. So that's what led to one of the most important breakthroughs in AI. Instead of compressing everything into a single vector, what if we could have the model attend to different parts of the input dynamically? This insight led to development of the attention mechanism. So more attention is all you need to focus more on important words. And move to the next. Did you get it?
Yes, I understand the need for this attention. So, can you elaborate and explain to me what this attention is exactly?
Of course, it would be my pleasure. So before even the transformer has entered into this, the attention has come because we had a major problem to solve, which is the context issue. We have solved the memory issue by bringing LSTM and GRU, but we have another new problem, which is fundamentally the context issue. So that's where in 2014, the attention mechanism was introduced. So the next question that comes is, how does this work? You can see the mechanism architecture. So you can scroll down a bit. So the question is, how does this work? So instead of relying on a single context vector, attention allows the model to look at the hidden states of every input step. So what does this enable? The model learns to assign weights to each input word that you can see on the screen, paying attention only to the most relevant parts when generating each output word. So why is this so powerful? It solves the information bottleneck problem. Instead of forcing all information through a single context, the model can directly access any part of the sequence when needed. So this dynamically improved performance on long sequences and complex tasks. It's like having a researcher who can flip back to any page of their notes instead of relying on a single summary. How it is.
Okay. Uh, attention allows the model to look back and assign weights. Is that correct?
Perfect.
Okay.
Absolutely.
So, is there a visual way to imagine what the weights would look like to the model? For instance, when translating, would it highlight certain words?
Exactly. Imagine it as a dynamic highlighting. For each output word, the brightly highlights the most relevant input words. Just imagine, try to imagine that. So allowing you to pinpoint exactly what information to focus on. Yeah.
Okay. So what comes after? What is the evolution of attention?
So that's the obviously attention has to be crazy now. So that led to self-attention, and eventually it led to multi-head attention. So self-attention takes the concept further. Instead of attending from output to input, okay, the model is the important of all other words within the same sequence to better encode each word's contextual meaning. So next question, because now you understood what self-attention now is a multi-attention. It allows this attention process to happen in parallel multiple times. So letting the model focus on different types of relations simultaneously. So why is this important? So a word's meaning often depends on other words in the same sentence. So self-attention capture these relationships correctly, while multi-head attention lets the model learn different types of relations, syntactic, semantic, thematic, all the same time. You see how crazy it's becoming slowly? You are one side in self-attention, capturing the relationship correctly within the same word, same sentence. A word's meaning often depends on other words in the same sentence. You know, that's what the overall sentence context we say. And your sentence overall context has been captured by self-attention, and your multi-head attention is taking care of the syntax of it, semantics of it, and thematics of it by doing the parallel multi-head attention, by doing the parallel processing at one go. This has changed the entire game.
Okay. For my further understanding, multi-head attention lets the model focus on different relationships, right?
Yes,
So
and
based on this, yeah. So based on this, could you like give me a hypothetical example of two different types of relationships that the two different heads might learn for the exact same word in a sentence?
okay, that's a nice question and nice way of dealing with things for the better understanding. Okay, so you wanted one for syntax and one for semantic similarity.
Yeah, that would work.
Okay, so then let's take this example. Oh, this would, yeah, for the bank of the examples. That's the sentence. Let's take the bank of the river, quote unquote. One had must learn its syntactic role. Next river. Another might learn its semantic meaning distinct from the financial institution because they have the bank, which says next to the river, and another head might learn the semantic meaning, which is says it's a distinct from a financial institution. So each head captures a different contextual aspect of the same sentence. How brilliant it is!
Yeah, that example was very good. The bank of the river. Nice. Uh,
Yeah,
okay, so can you summarize on why does context awareness matter so much?
yep. Because the same word can mean completely different things depending on the surrounding context. Traditional models struggle with this ambiguity, but attention mechanisms finally enable models to understand context dynamically and accurately. So whatever these traditional models have suffered, so that is what is context awareness, and fundamentally we are able to get it using attention, self-attention, and multi-head attention has solved the problem. And now this is going to lead to a different era. Let's brace yourself for that.
Yeah. So, to summarize, what was the most revolutionary development among all the developments we have had so far?
Yeah, let's discuss that. So let's get into that brilliant era in the next slide. So in 2017, Google researchers published Attention is All You Need. Just a minute, yeah. Attention is all you need, introducing the transformer architecture. So what made it so radical? It completely eliminated recurrence and relied solely on multi-head self-attention. Multi-head self-attention. So why was this so revolutionary? Because it wasn't sequential. It could be massively parallelized. What does this mean? Instead of processing words one by one like ordinance, transformers could process entire sequences simultaneously. This drastically reduced training times and enabled the creation of enormous models. So, how significant was this? So the transformers became the foundation for virtually all modern large language models, and it solved the sequential bottleneck that had limited RNNs and enabled the scaling that led to GPT, generative transformers, and BERT, bidirectional encoding recurrent transformers, and all the language models we use today. Eventually, what I would like to say is your transformers come and kick the RNNs.
Yeah. Now that we talk in retrospect, it really was the most important development. So the phrase "attention is all you need" is also iconic. So
Yeah, brilliant. That's
I'm also
awesome.
curious about this thing. What was the initial reaction or skepticism from the community, AI community specifically, when this paper
Yeah,
was first published, given its radical departure from recurrence?
yeah, perfect. Actually, yeah, this is actually a brilliant question. So there was a huge initial skepticism. I'm seriously telling, and people were not paying much attention. So they were busy working in their same fixed input size and fixed output size machine learning models as it is. So, but at the parallel time, there were a few persons actually understood the power of this, of course, and they started building their models parallelly using this transformers. I know whom I'm quoting. You open air, and few other models, Anthropic, and few other models are parallelly picked it up. They did not take time, they did not show the skepticism, and they started building on it. But however, this massive parallelization and groundbreaking performance quickly proved its power and fundamentally changing a sequence modeling forever.
Nice. So, how do the modern language models
But
work?
but just to remind you that even I'm the one, I think in 2017 this paper was released, and by 2018 it's completely available over the internet. I started reading this paper. I'm unable to think where it's gonna take up, but I was very sure that we are basically stepping into a different world altogether. And I still remember how excited I was, and I have basically discussed and about this paper, and we have internal discussions with my team members, and you know some of those people.
That is
Cool, yeah,
brilliant to hear. Yeah.
yes.
So, as I was
So
asking,
see
how does
how we are discussing now about the Gemini diffusion model, which is again the radical shift from auto regression. The same way we were discussing about the transformers, but not on the YouTube, not on LinkedIn, but in our office space on the transformers, which is a radical shift from the RNNs sequence 1 to parallelizable time. So it had happened that time, now it's happening now too. There is not much of a difference. Yeah.
Yeah, it really was a historical moment, and it took people a lot of time to understand that it is going to change the world also.
Yeah, exactly.
Yeah. So, using this, just explain to me in short, how does these modern language models work?
Yeah, that's what. So we can move to the next slide. So again, the transformer architecture, particularly its decoder, is still auto-regressive. I'm been repeating this is very important because again, because of this auto-regression, we have achieved what we have done so far, but still it comes up with some issue that we'll discuss later. But we should all be thankful for the auto-regression first. Then again, we will fight with the auto-regression later. But for now, we are thankful. So now it generates text by predicting the next word based on all previous words. You know this. So one token at a time. One token at a time. So what models use this approach? OpenAI's GPT series, Google's Gemini, and our Anthropic Claude, Llama. So, and most other language models, large language models. So why is this approach so successful? So it combines the parallelizable meaning of transformers. Okay, we have radically shifted from the sequence to parallelizable meaning of transformers with the proven auto-regressive generation strategy. The result, models that can generate incredibly coherent and contextual text by building everything they have written before. Just to summarize for your benefit, where we have started, the first biggest problem is to have at least a variable length input and output. For that, we have moved out of the artificial neural networks, the vanilla neural networks, to other stuff. So the biggest issue at the initial stage is to add a little more memory. The next one is add to a little more memory. Then we got LSTMs and GRUs. Then the next headache is to have context. So to add the context, we have added one more layer to it, which is your attention. And you want to make the context so powerful. So you got the self-attention and you got the multi-head attention. You want to do it in a much better way. You got the multi-head self-attention. We are not happy even with that. So we don't want to do the sequential one because it is not capturing the entire thing properly. Then we have gone for one step ahead and we have built a transformer which has a parallelizable training. Now we are bringing this parallelizable training transformer and bringing an auto-regression aspect of RNN. We are not bringing an RNN. RNN has been thrown out completely. We have built a transformer which consists of parallelizable training, but the auto-regressive aspect of that has been taken for the prediction. And we have made the most powerful one, which is a large language model with the inclusion of multi-head self-attention and with the inclusion of the decoder encoder techniques that I have built before. You see, every aspect that we have worked to solve some or other problem has built a brilliant large language model, and no YouTuber would tell you because fundamentally they would have not known this. So
Makes
coming to
sense.
this auto-regression model, So this, and one example, this is how an auto-regression works. The new prediction is always based on the previous prediction. So that's what the mathematical equation that we have added there. Yes. So y1 is the new prediction, and it's depends upon, and it's multiplied with the coefficient or the parameter with the y sub t minus 1 is your previous prediction. So that's what the auto-regression fundamentally means. And this auto-regression is widely used in your time series forecasting, time series auto-regression, ERIMA, auto-regression, ERIMA. So all these models are auto-regression, and we're thankful to that time series models, which has given brilliant large language models for now. Yeah.
Yeah, can you highlight what are the main differences between these approaches?
Between auto-regressive and non-auto-regressive?
Yeah.
Is that your question? Yeah. Can you move to the next slide, please? So auto-regressive models generate each element based on previous elements that I've shown a mathematical equation. Y sub t is equal to beta sub 0 plus beta sub 1 multiplied by y sub t minus 1 plus alpha sub 1. That's one of the mathematical equations of auto-regression. So they are inherently sequential during generation. Non-auto-regressive models, but this is very, very important. See, I just take a little more time. Now, recurrent neural networks we have used. Okay, so when we talk about any model, we have two aspects to it. One is training of a model. Second one is inference of the model. Okay, now prediction size. Now, an RNN is training is also sequential, and when you're predicting something is also sequential. This is because it's a fundamentally auto-regression always. Then we have made a transformer. When I say we, Google has made it, but of course they are also part of our humanity. So I'm saying we. So when we have made a transformer, what radical change that we have done it is the training is no more sequential. The training is parallelizable. But still, this large language model prediction is sequential only because it is again auto-regressive. What are you trying to understand? What I'm trying to say? This model consists of training and prediction. Okay, the training of large language model is parallelizable, but your prediction is still sequential because we are following the auto-regression. So, and because of that, next token prediction, because the next token, which has the highest probability, will be predicted, will be the next token in that entire sentence. Everyone knows that. That's how LLMs work. Okay. Now this next token prediction is completely sequential, and it is auto-regressive. So because of this auto-regression, we are able to create what we have done so far. But so a non-auto-regressive model generates all elements simultaneously without relying on previous elements. So what are the trade-offs? So auto-regressive models typically produce higher quality, more coherent outputs because each token considers all previous context. Non-auto-regressive models can generate much faster because they work in parallel, but often sacrifice some quality for speed. So this speed difference becomes crucial for real-time applications. Of course, some of the LLMs take a little time, but that is not, it might create some issue for us because when we do a real application example, you want to create a mission translation. I want to speak to you. I know only Telugu, you know only Russian. Then I want to speak to you live, and it should happen at a fraction of a second. There should not be any time delay. Can you rely on a normal auto-regressive model? I don't think so, because I need to wait for some 20-30 seconds for the response, and that's what is happening with the Gemini Live. So we need to come up with something much better. So this is what the biggest problem. Yep.
Uh, it was a serious lecture. But you mentioned that non-autoregressive models would sacrifice some quality for speed. For
Obviously,
which, yeah. So for which
but we can
specific
make it better.
real-time application? Sorry.
We can make it better as we required.
Yeah. So for that, in that train of thought, so can you tell me for which specific real-time application would that speed gain be so crucial that slight reduction in quality is acceptable?
Yeah, so that's what basically I was talking about before, the same example. So I want to use a Gemini Live. Okay, example.
Mm.
So you know some language, I know a different language. I want it to happen at the real time, live, without even a fraction of second of delay. And the present one do it even after using the most powerful GPUs, we are unable to do it because Gemini can't. Still, it is taking about 10 seconds because that we use Gemini Live for the real time station. Still, it is taking extra 10 seconds of time to respond back. So that's one example where we can do it, because once we get this non-autoregressive model which responds back in a fraction of second, you will see a most powerful vision translation live. So real-time speech synthesis or live conversational translation. So for this immediate fluid interaction is paramount. So a tiny quality trade-off for instant response is highly acceptable. But however, we can make a better, a powerful, non-autoregressive model, and it is not okay.
Yep. Let us do it just like every other model that we have done until now. What are the biggest drawbacks of autoregressive models?
Yeah, we can move on to the next slide. So as I've been mentioning, as we have already discussed multiple times, the latency. We can move on to the next slide, please. Latency. So even with powerful GPUs, generation is sequential. You must wait for the first word before generating the second one. You're getting the point what I'm trying to say? Let's imagine you have to make a 600 tokens. So you have to wait for the second. If you have to wait for the first one to be generated before the second, and the second one should be generated before the third, and the third should be generated before the fourth, and so on, so on, so on. This is what I'm saying. The model consists of two aspects. One is training the model, and second one is using inferencing, using when it is generating the tokens. So now the present LLMs training is based on the transformers, which is parallelizable training. Perfect, brilliant. Whereas your RNN is training is also sequential, and your inference is also sequential. So at least we're able to solve one problem. Your training is parallelizable. But what about the second one? Second one is still generating sequential. So now this is the biggest problem. So why is this problematic? For real-time applications like conversations or interactive systems, this sequential dependency creates a noticeable delays. Users expect immediate responses, but auto-regressive generation inherently takes time, and this became the new bottleneck that needed solving. Now, do we need to completely remove the old one? Not at all. As RNNs has been used for a lot of other use cases, so time series forecasting, etc. Similarly, your existing autoregressive large language text models can still be used for a lot of use cases. But when it comes to the real-time applications like conversations and interactive systems, we need to work on. So now, did you get the point?
Yeah, I got the point. So, what is the solution for this one? What is the promising solution for latency?
So that's what everybody is working, and Google has already worked it, and few other companies has worked it. So we can move to the next slide, and we are majorly working on the diffusion models. Of course, you would have heard the diffusion models in an image generation, basically from the image side. So that's where we would have heard the
Yeah.
image, you would have heard the diffusion models. But here, what we're talking about is the diffusion model for text. So diffusion models represent a completely different approach. How do they work? Inspired by thermodynamics, crazy stuff. I hope you don't know much about thermodynamics, but we love it. A diffusion model starts with a pure noise and learns to gradually denoise it over a series of steps into coherent output. Now, why is this better for speed? So these denoising steps can be performed more in parallel rather than the strict sequential dependency of autoregressive models. So what's the key insight? Instead of building output token by token, you start with a rough approximation and refine the entire output simultaneously. It's like sketching a picture, gradually adding details everywhere at once rather than drawing it line by line. So that's what is the brilliant diffusion model that you can see on screen, the technical architecture.
Yeah. So I have also done engineering. I have also studied for JEE. I know thermodynamics. And your example for diffusion, it's the first time I'm hearing, and it is fantastic. But is there a simple and non-technical way to explain this process of diffusion model, this process of denoising, perhaps by relating it to something visual or creative that people do?
Yeah, so probably we can take this example. Imagine an artist who unblurs a noisy image, and they don't draw it piece by piece. They gradually refine the whole blurry picture at once. So step by step until it becomes a clear, finished artwork.
Yeah. What is the relationship between Gemini and diffusion?
Yeah. So we can move on to the next slide, please. So this is where, so this can be confusing, as I've told you earlier. Gemini refers to the Google family of powerful, natively multi-models built on advanced transformer architecture. So diffusion models are a separate class of non-autoregressive models. Now, are the same thing. Now, Google researches both areas. They are distinct technologies. While there isn't a specific model which is primary public offering, both Gemini Diffusion is not a public offering at this moment. It's a research model they have. So it's important for us to understand that Gemini Diffusion model is a new model from the Google's Gemini family, where they have used a non-autoregressive technique as their large language model or text-based model. So it is completely different than the previous Gemini what they have. Now it is a different model, which is Gemini Diffusion, which is a non-autoregressive, which is very, very powerful. You can see on the screen how it looks at the moment. It is available for testing for only trusted testers, and fortunately, I got an opportunity to test it, and of course, we have tested it together, and you know how powerful it is. And I would like to thank Google DeepMinds for giving me this opportunity to test it. A revolutionary a brilliant, the first of its own model. Yep.
Nice. Yeah, so we know that Google is researching both of them, Gemini, the family of models in Gemini, and Diffusion also. Uh, what do you think are the primary challenges or theoretical hurdles in combining the strengths of a transformer based model and with the generative process of a diffusion model?
The big hurdle of the big hurdles are bridging the discrete text with continuous data diffusion. So ensuring your long-range text coherence and managing the immense combined training cost. So this is fundamentally comes at cost also. Yeah.
Okay. Let us move on to the main stuff. What is the fundamental difference between in how they work?
So fundamental difference between
How the traditional LLMs and diffusion work?
okay. So can you move to the next slide, please? So as we have been discussing earlier, an auto-aggressive LLM builds. Move to the next slide, please. An auto-regressive LLM builds its output sequentially, token by token by token, and always conditioning on what came before. A diffusion model refines its entire output simultaneously or a fixed number of steps. So how can we visualize this difference? So it's like the difference between writing a sentence, one word at a time versus sketching the entire picture and gradually adding a detail everywhere on. So what we do as a human, we behave like an auto-regressive LLM. We write a sentence one by one. When we are creating the picture, we do it in an auto-regressive way. So both approaches have their strengths, but they solve the generation problems in fundamentally different ways. So that's what you can see on the screen, the traditional LLMs versus the diffusion models.
Okay.
Yep.
So, what is the primary advantage
Of diffusion models?
Yep, the benefits of diffusion model basically.
Can you move on to the next slide? So reduce the most important and then primary advantage is the reduction in latency. So can you move on to the next slide? So reduced latency during inference. That is very important for some of the use cases. Because they're not strictly sequential, so they can potentially generate entire sequences much faster than autoregressive models, which have they proven successful. So they have already shown state-of-the-art results in image generation, but we are majorly focusing on the text generation in a much different way so that we can have real-time conversations. So what about text generation? This is an active area of research, and while diffusion models are still being refined for text, they show promise for making large language models much faster for real-time applications. The potential speed improvement could be game-changing for interactive AI systems. As you can see on screen, Claude, ChatGPT, and Gemini diffusion model for the research application, and you can see the time they have spent from 28 seconds, 36 seconds, and then 6 seconds. And similarly, we have also tested for multiple test cases, as fortunately I got an opportunity to test this state-of-the-art Gemini diffusion model as a trusted tester for Google. So we have tested it and we have clearly noted down the time spending. It's fundamentally not more than 1 to 2 seconds. It's like The moment you press on the generate button, and you can see the response there. Yes.
Yeah, so as I understand, diffusion models are state of the art in image generation as of now.
Yeah.
So, what makes image generation particularly well suited for diffusion compared to, let's say, generating long form coherent text, which is currently in research? What are the unique challenges for text?
So fundamentally, when it sees as a human, when you write a story, you write word by word. But when you make a picture, when you draw a picture, you do it in a different way. You make a rough picture. On top of that, you build it. The same way, images are continuous pictures, pixels. So making diffusion's gradual refinement is is where it will go. As text is discrete words, so making that smooth denoising is hard. So all the text needs a strict grammar and coherence. Major challenge for diffusion, but of course, we can overcome that as we have done a lot. Yep.
Yeah, so we have covered all the innovations from 19th century to present date until today.
Yep.
I want to ask you, based on your experience and intuition for the future, where
Okay.
is AI heading?
So actually, I'm fortunate to see from the classical machine learning to the deep learning, RNNs, STMs, transformers, and then attention mechanisms, and our autoregressive LLMs. And now I'm fortunately to test this as a test for the Gemini diffusion also. So, and I have built a production ready applications, and majority of these technologies I have built, and I'm literally fortunate to be this. But now, with this experience and expertise, what I see is the future involves synthesizing these ideas. We are moving towards models that are not only deeply multimodal like Gemini, but also leverage on non-autoregressive techniques like to be faster and more efficient. So what will this combination enable applications that require real time? So multi-modal AI interactions. Think of AI that can scientifically process text, images, and audio, responding instantly. How brilliant be? What you literally, if this is done, you can see a robot with all the human type of intelligence, and he can literally respond back to you on real time. What would you want? This can literally change a lot of things, because you can have an agent, you can have a virtual assistant who can literally contact you with in real time, in a brilliant way. That's what I see is going to happen. So fundamentally, whatever breakthroughs that are happening at this moment revolutionize the robotics too. The robotics, what we've seen before, instruction based, now it will become a predefined set of instructions that you used to have completely, but now the robots will become intelligent. And what I see is the moment the quantum computing is growing in a very fast way, the moment you have a quantum computing, which is a brilliant, the superior hardware, when this superior hardware meets the superior software, which is AI, that's it. The biggest era of the human kind is going to be witnessed.
You are giving me an existential crisis, but I also know fearing this is not going to solve anything. I will obviously, as well as like everyone else, keep learning, keep upskilling, and be there with the times, basically.
Yeah, that's perfect. Yeah, we can move on to the next slide. Yeah. So anything else you have before we go for Q&A?
Uh, as such, nothing else. But I
Okay,
have
so
a
then,
question though.
but before we
As
go to
in,
the next question, yeah, what I would like
yeah,
to do is let me summarize the entire
yeah. We should do
uh,
that.
like entire stuff that we have discussed so far. So we have started with vanilla neural networks, which is fundamentally good at handling fixed input variables and fixed output variables. And for us, the biggest problem there was to handle the variable sized input and variable sized output. So now for that, we have come up with different types of thing, which is a recurrent neural network, which can fundamentally do a sequential training. The model will be trained on sequence, and then the output is also prediction also based on the sequence. Okay. Now it is good in dealing some aspects. Even in RNNs, we have the many RNNs as well as the one RNNs as well, to one RNNs also. Okay. Now with the neural network, we are able to solve, but as while we see the problem, we got the another problem, which is the memory problem. Now, how will we fix the memory problem? So the memory problem is fundamentally we have worked out by bringing new gates, input, output, update gates. So by doing that, we got a new architectures which are LSTM, and so as LSTM is little complex architecture and it is little complex to train and it takes more resources, we have a much simpler one, GRU, gate recurrent unit, GRU unit. So with that, we have to solve the memory issue at this extent. Now, a new issue has come after solving this memory issue, and we also fix the vanishing issue. After doing that, we have a new issue. Is that as a context issue? You want to have to become better and better, or you don't want to settle on this. The moment you don't want you're dead. We don't want to do it as an AI community at all because we are going to drive this world to the different level. So we don't want to rest down at one place. So that's the reason we want to make it much better. So now we want to solve the context problem also. Now, how do you want to solve the context problem? In 2014, our AI community, when I started fortunately in machine learning, when I started in 2014, parallelly those guys have released the attention mechanism. See how coincidence. You see the coincidence? So I got to the machine learning. So that's the reason I want to bring machine always machine learning, deep learning to everybody. Just kidding. So now, in the we got the mechanism to solve the fundamentally of content. So that attention is not enough to go one step ahead. Attention is purely connected with output to the input word sentence. So then we wanted to have a self-attention, which is majorly focused on the sentence itself. What to word it within sentence. Then from the self-attention, that's not enough because you want to, this particular sentence can have, a single word can have a multiple contexts based on in a different way. Example, the syntax. So semantics. So that's the reason we have got the multi self-attention. Let's do the self-attention in a multi-way, a parallel way, so that we can from the semantic perspective, syntax perspective, and let's see which makes more sense at the end of the day, the overall context. From the macro level, we have come to the macro level, the micro using the multi-head and then self-attention. So now at least we are able to solve the context and we became much powerful. Now, because we are solving the problems one by one. First, the variable one, fixed length, we have solved the fixed length issue. then we are solved the memory issue, then we are solving the context issue. So from there, we are going to the next aspect. Fortunately, by the time we have reached 2017 and we are really working on computation models and artificial focus transformers. So fundamentally, this transformers works on a parallelizable trend. So, and which again is of encoder type of network, as we have discussed previously. So RNNs used to have this encoder decoder network for the machine translation, and we have taken the same encoder decoder type with the parallelizable training, and that has become our transformer. Now what we have done is what GPT has encached immediately. OpenAI has encached this immediately, and parallelly the moment Google has released this, they have taken this, they have taken the transformers, they have taken the attention mechanisms, multi-head attention, self-attention, and some aspect of auto-regressing from recurrent neural networks. That combined thing they've made they've released in 2020. So this is what has become the generative pre-trained transformers. And this, what the LLMs have changed everything, and now it is becoming without LLMs that we have reached that stage. You write a mail using your LLM, you write a word using your LLM, you do the research using your LLM, you do the Google search using your LLM, you search everything using your LLM, and you search your documents using your LLM, you search your clothes using your LLM, you search your images using your LLM. So everything is with LLM. So now what kind of LLM we are using is auto-regressive LLM with a transformer plus the multi-head self-attention. Now we want to fix another problem, which is we want to have a real-time, zero latency translation or conversation. And that's where we brought a new type of, at least not we, Google has brought a new type of new type of language model, which is a non-autoregressive, a Gemini diffusion model, which can respond back to us within a fraction of a second. And that's what we are seeing. We have tested it, and it is working. And that's where from artificial neural network, we have reached to non-autoregressive language model. I hope you got it.
Yep. Actually, I was going to ask this question only, but you already summarized all the things that I was going to ask. But still, I have framed this question very properly just now. So let me ask it. As AI seamlessly weaves into the fabric of our existence in our daily life and in the society as well. As you said, becoming multimodal, instantaneous, and almost omniscient with the current knowledge at least. What will it mean to be a human in this world, where intelligence is no longer solely our own, and how might our shared values adapt to this profound new reality?
So why are you going into the philosophical questions in our technical? Yeah.
Because you answered all the things. Actually, you answered how our daily life is going to change and all.
At this
But I
moment,
want
I am here to.
Yeah.
At this moment, I'm here to advocate AI in all the way possible, because there are almost a lot of people who are trying to resist AI and then stop the movement of AI. So we are here to advocate AI. However, you have asked this question, I would like to answer. Yeah, in daily life, so we will experience ambient intuitive assistance across all senses, making interaction seamless. So this means hyper personalized services. You will have your own clone next to you, which is a digital clone. You can have a digital twin. So probably you can call it as identic AI. So you will have your own identic AI. So even if you know, as per our cosmos, we have some theories. You have the parallel universe. Okay, in the parallel universe, somewhere, as per the quantum mechanics, you will have your quantum twin. You will have your own quantum twin somewhere. that guy is, you're here, so similar quantum twin, exactly your quantum twin will be there in the somewhere, some other universe, and you and he will be reactive based on each other's responses. So the similar way you can have your own identity at your place, your twin, your clone. So probably we will reach
This is
that
terrible.
stage, of course. Yeah, so we already started building that kind of solutions. As per the societal structures, expect redefined job markets demanding constant upskilling, and new economic models like universal basic income and critical focus on ethical governance is becoming a bigger thing, and data privacy and mitigating algorithm bias to ensure equitable benefits for all. So basically, I would like to tell one example. So I think previously I forgot the company name, but at least I remember the location in US, United States of America. One particular client has sued one company for saying that your model is biased for particular one thing. So then court has fined them with huge money. So now as you build, you have to make sure your models are governed properly before you leave it to the external world. So you need a proper AI governance. So finally, to conclude, it will deepen what it means to be human, emphasizing our creativity, empathy, and critical thinking, and qualities AI augments, not replaces. That's what you have to remember. And our shared values will adapt by prioritizing ethical AI development, equitable access, and purposeful collaboration between human and artificial intelligence, steering us towards a future where technology truly serves humanity. But I want to end this with one important point, saying that the moment you're free of doing a manual, simple, routine, repetitive task, your brain has some memory to do much bigger tasks, and you can explore the universes, you can explore the cosmic energies, quantum mechanics. So probably we will have more space to connect with the extraterrestrial bodies, so that we can communicate with the external worlds. Because in this universe, where you have the billions of universes, millions of galaxies, billions of solar systems, billions of planets, probably there will be somewhere one life living for you. Probably we need to speak to them once. That will be only possible if you're free of all these repetitive routine tasks. Thanks to the AI, it will make us to do that.
Yep.
Yeah. So
Outsourcing thinking also, so that we could focus on more important goals.
exactly. So that's actually very important to do. Yeah. So do you have any questions specific to Gemini diffusion model? So where you can access and how you can access all that sort of
Yeah,
information?
I want to know where I can access, and when will general public get access to it as well, and how is this going to like become a replacement, or become a better use case for things rather than
Yeah, I
normal
think
LLMs.
yeah, exactly. So before we even go into that, so if you want to understand, just because we can understand the present LLM architecture ecosystem, then we can go for the other one. See, I would like to say that you have GPT-1, GPT-2, GPT-3, GPT-4.
Hmm.
These models architecture is decoder only.
Yeah.
Okay, decoder only transformer, and it is auto-regressive. And their generation is left to right generation, a casual attention mechanism, what we have seen. Then we have the Claude, which is Anthropic's Claude. That is again the decoder only transformer and autoregressive mechanism. It's purely based on the chat GPT. It's purely based on your constitutional AI training. Okay. Then comes Llama, Llama 2 and Llama 3. So that's again the decoder only. Then it's also autoregressive. Then you have the Gemini. So Gemini, you have this also an auto regressive, and it is bidirectional encoder change. So then you have the T5, encoder decoder, which is encoder decoder. This is a full transformer architecture. You can get these in Hugging Face. Then you have BART. So that is again encoder decoder type. This is denoising. This is a different one. Then other models we have BERT, bidirectional encoder recurrent transformers, which is purely encoder only, which is bidirectional and understanding tasks only. So these are some of the present LLMs architectures, and these are all autoregressive. These are all text-based, these are all autoregressive. Of course, Gemini is multimodal, but still it's not autoregressive. Yeah. So any other questions do you have specific to Gemini diffusion before we wrap up?
Yeah. Final thing. Where can we find the diffusion model, and when will it be released for public use?
Yeah. So first, let's try to, as we have discussed earlier, Gemini diffusion is a text diffusion. At this moment, it's a language model created by Google DeepMind. Okay. Now, the difference, as we have discussed earlier, traditional autoregressive language models generate text one word or token at a time. So this sequential process can be slow and limit the quality and coherence of the output, as we have discussed earlier. So diffusion models work differently. Instead of predicting text directly, they learn to generate outputs by refining noise step by step. So this means they can iterate a solution on a solution very quickly and error correct during the generation process. So this helps them excel the tasks like editing, including in the context of math and code. So there it will be very, very powerful. When you integrate this particular thing with the live pair vibe coding, it will become very powerful. So at the end of the day, coding is going to become much powerful. So yeah, next question.
That is it from my side.
Okay, that's good. So I just want to add, before we close it up, so I just want to add a few more points, such as where you can find this. That's what you have, as you have already asked this information. So this Gemini diffusion model, which was created by Google for the text generation, at this moment is under testing by trusted testers, and I'm the one of them. And so at this moment, it's not open for the public. So once it is tested, they're collecting all our feedbacks. We have shared enough feedbacks for them. So once it becomes powerful, they'll start release it soon. But for now, it is only for testers. Now, at least you can find it in Google DeepMind's Google Labs, just to understand what it is. And so next question that you're saying is Gemini diffusion a thinking model? Of course, at this moment, it's not a thinking model. Okay. So probably in future they can make it, but Gemini diffusion is currently an experimental text generation model focused on diffusion technique. So it's not unlike Gemini 2.0 and all those are complex reasoning, understanding, and conversation. So they are thinking models, but Gemini diffusion is not so. So
okay, in that context, I would also like to ask which model is this Gemini diffusion currently being compared to?
So that's what normally we compared with Gemini 2.0 flashlight, because the Gemini diffusion is not large at this moment. Once it is large, probably you can compare with the larger models. So you need to compare the time spans with these models particularly. And we have done the same, right? We have done so much time. The same prompt we have given it to the Gemini 2.0, 2.5 flash, and with the diffusion model as well as the GPT models. And we can see the literal difference, at least 2 to 3 times of time latency difference we are able to see. So, yeah.
Yeah, so while I was testing this diffusion model, I noticed something that the tokens per second was changing dynamically. So why does the diffusion model's token per second change that dynamically?
Because the generation speed token per second, but of course you will, by and large, you'll have the similar one. It won't change much, but still it is dynamic. Diffusion can vary, but not hugely. So factors influencing this include the length of the prompt, one, and the length of the generated text, two, and the current system load, among other factors. So these are the major reasons for that slight change in the tokens per second. But however, we have witnessed the fastest models. Yeah.
Yeah. So in that train of thought, before we end the things, why don't you tell us what are the current limitations or challenges of Gemini's diffusion?
Yep. So it may not perform at this moment. It's under testing. It's under completely, absolutely testing. So it may not perform as well as a highly optimized auto-regressive models on all types of text generation tasks. So that's a reason, as a trusted testers, our feedback from the demo and testing is crucial for them to identify and address those issues.
Yeah, that is it from my side.
So that's brilliant. I think if there are any other questions from anyone, so please don't hesitate. Just put it on comments, and we would like to respond to those questions, because these are the different times. Now we are quickly getting into a different world. See, what is my prediction at this moment? Eskid, you can also share yours. Now we are lacking some abilities. Okay, what are those abilities at this moment? Okay, you're doing good in doing things at some aspect. Okay, you're able to fetch the information, the big databases, you're able to speak, you're able to write the code using the LLMs. But we are lacking the real time. In translation or in writing the code, there is a latency. But some of the use cases, because there are a lot of use cases which requires immediate response. Example, if you want to make a virtual assistant using LLM, that has to respond quickly. It should not take 10 seconds or 20 seconds to respond back. It would be boring for a human to wait for a robot. So now how will we solve this? And that's where we are working towards diffusion models, and that will come and it will solve the problem. So eventually what we're trying to do is we are making things better and better to completely enable this world as AI, an artificial intelligence enabled world. That's what my prediction. What's yours, Escape?
Yeah, so from my side, obviously I'm not as experienced as you to give any bold predictions, but I think people everywhere I see, even my colleagues who have graduated with me, are going into some existential dread, thinking that AI is going to take away the job, and AI is going to take away everyone's job, not just software engineers. But these kinds of things have already happened in the past. Nothing, even though it's going to take away some kinds of jobs, humanity as a whole will always bounce back. This financial systems, economics, nothing is going to collapse. We are going to just pivot into some new era. That's all, and which will be obviously an advanced one.
See, as a human, we have evolved. As a universe, will evolve. So that's it. Just be part of this evolution and embrace it. That's it. So don't think much.
Yeah.
Just go with the AI flow.
Yeah, thinking of a goal is only going to give you a headache. Enjoy the process. Think of the process and enjoy the process.
You put the more focus on process and put all your efforts into it. That will make you have more fun with the AI than just being scared of what's going to happen. But anyway, it's a brilliant conversation. I hope you got the entire point where we have started and where we have come and where we'll be going as we go ahead. And thanks for being part of it. And we highly appreciate your time and efforts to be part of it and then asking the questions. And it's very interactive. I hope people who are watching also liked it. If there are any questions, just please don't hesitate to put it in the comments and we will respond to it surely.
Also, Chandra, thank you so much for organizing such a long webinar live. Thanks a lot.
Thanks, man. Take care. Have a great time with AI. That's cool. That's vibe coding. But what if we amplify that vibe, make it a team sport? So, and we are not just coding with AI anymore. We are doing a pair vibe coding. So we call it as pair vibe coding. For me, pair vibe coding is just like conducting an orchestra. We will explore UI UX with Google Stitch and launch ideas fast using bolt.new or microsas setups.
Jay, the pair vibe coding is where the team creativity meets the AI precision. We'll harness the powerhouse like Gemini 2.5 Pro and specific Mistral AI agents.
Hello! Pair vibe coding is the next wave of innovation. Imagine crafting stunning UX with global development or diving into Web3 with multiverse as a unified team.
Hi, pair vibe coding breaks down barriers. We'll build MVPs with Replit, deploy it on Vercel, and even manage asynchronous tasks with Google's tools.
So before we wrap up this webinar, so I would like to go through the pair vibe coding that we have coined, and we are working on that. So as part of a pair vibe coding series, we have started with the Google Stitch, and so next week we'll be using the another tool for the pair vibe coding, and we'll be building a brilliant websites by doing the pair vibe coding. I hope you'll join that and you will enjoy and learn the pair vibe coding with the different types of tools. And I hope you enjoyed the present the series, present pair vibe coding series, and as well as the Gemini Diffusion live webinar too. And just keep watching, keep learning, and then keep subscribing, and then commenting it if you have any doubts. Until then, take care and have a great time with AI.